So now, in short, we will see what is the difference between the one dimension, two dimension, three dimension. Then we will go for the superficial expansion. Okay. So solids on heating, whether when one dimension is there, when the one dimension solid is given, in that case, the particular length increases, and that increase in the length is known as linear expansion. Okay. Then second dimension, or the sorry, two dimension solid is there, then the particular area increases, and that increase in the area is known as superficial expansion. And last is nothing but the three dimensional solid. In that case, the volume increases, and the increase in the volume is known as cubical expansion. Okay, so this was the comparative study of the thermal expansion, which we must know in short, because if these things are kept in mind properly, you can also derive your own equation. Okay, means what? If the linear expansion is there, you will take the linear, means initial length you will take, the change in temperature is denoted by delta T, and the final is given by the another alphabet. It is not necessary that if the teacher has given on the board that L0 is there, L is there, no, you can write it of your own also. Okay, means the original length can be named by the another alphabet, initial is named by the another alphabet, and the your change in the temperature delta T, but the meanings must not change. Means if the delta is there, you must use the delta only. Why? Because it is infinitesimal small change over there. So don't invent or discover the new operator over there. Okay, so if you write, you can also write the answers of your own. You can also derive the answers or the equation of your own. If the basic concept is there in your mind, you can do anything. Okay, for example, I took any one dimension rod over here. You can take any one dimension metal rod, or not rod, anything whichever you like. Okay, then superficial expansion, when the area of the solid increases on heating, the thermal expansion is known as the superficial expansion. Okay, now this superficial expansion is nothing but the expansion in area. Okay, means two dimension area is there. So this is your original area, yes, and after expansion of this area, how it will look? This is the change in length or change in the area. That is also given with the help of delta S. As it is the superficial or the surface area, we will take this change in delta S only. Okay, because it is easier to understand, and this is your original area, and the change in area is given by the new area is formed, that is S. Okay, so the equation from the diagram you can write that delta S is equals to final area minus initial area. Okay, is there anything difficult in this? No. If you understand one dimension, two dimension, three dimensions are very easy. So I'm not going to waste more time over here by repeating the things again and again. Okay, so let S0 be the surface area. Okay, surface area original, or before heating, the surface area is given by S0. Then again, now without looking into the book only, we can write the change in temperature. It is denoted by delta capital T, by capital T, because this is the temperature, not the time. Okay, then next is what? Change in temperature or the rise in temperature. Use any one of the word. Meaning is same over here. Okay, let the surface area be increased by S. So increase in area, increase in area is given by capital S. Okay, again next is delta S be the increase in the surface area, then delta S. So delta is nothing but the increase in the surface area, and that is given by S minus S0. We know this very well. Okay, so now from this we also came to know that it is proportional to the change in temperature, and its original area. Okay, so the same equation we can write it for the surface, that is delta S is equals to S minus S0, and we know that according to the proportionality constant, the proportionality constant is known here beta, and it is denoted by S0 beta into delta T. From where this uh, equation, not equation, these terms came, they are nothing but the same as we have used in the one dimension case. Okay, there alpha was there, here only beta is there. And what is beta known here? It is coefficient of superficial expansion. Okay, here beta is nothing but the coefficient of superficial expansion. Okay, now everything is same as compared to the um, one dimension. So did you understand this? Is there any hard in this? No, nothing is there, no changes is there, only one dimension is increased over here, and respective alphabets are changing, and mathematical derivation is same. Okay, okay, now next is uh, finding the value of beta. From that same equation only we can find the value of beta, which is given by beta is equals to S minus S0 is nothing but the change in area upon original surface area into change in temperature. Okay, that is also denoted by delta S upon S0 delta T. Okay, same is there. In that case, it was delta L. Here L0 was there, no changes there. Okay, then everything is same. That the SI unit of beta is K inverse, but one thing is changed here. That if S1 and S2 are the two surfaces then of a solid sheet of the temperature, then T1 and T2 are the respective temperatures for them. Okay, as here two areas were there. Okay, they are having their respective temperatures. Okay, so the equation is going to change here, and so what is the change in equation? That is beta is equals to S2 and S1. In this case we have considered this surface area as S1 and this second is as S2, or in the same if you write, then it will be S2 minus S1. Okay, S2 minus S1 upon original surface is given by S1, and that is change in temperature, that is T2 minus T1. Okay, from where this T1 and T2 came? Because the original area was having the temperature T1, and T2 is the respective temperature of the second or the new formed surface area. Okay, so the next step, the same thing or the same equation can be written as S2 is equals to S1. Okay, 1 plus beta T2 minus T1, bracket close. Okay, so this is the equation for the new surface area which is formed due to the thermal expansion. So this was the superficial expansion, and what we have seen in this, yes, we have seen, we have already learned about it, that the original area was denoted by the alphabet S0, the change in temperature was denoted by delta T, and the coefficient of thermal superficial expansion came, that was denoted by beta. The SI unit for the beta was same, that is Kelvin inverse. Okay, but here slight difference is there, that here two terms came for the temperature, that is T2 and T1. T2 is the temperature of the final or the area formed due to the thermal expansion, and T1 was nothing but the initial surface temperature. Okay, so now we will see the next and the last thermal expansion, that is cubical expansion. Okay, this is your volume and the increase in the volume. Okay, so now here the same thing is there. We will see that okay, the solid body of the volume V, okay, volume V0, okay, original volume is given by V0, then again the rising temperature is denoted by delta T. Okay, then again uh, volume after the heat is supplied is given by V. Okay, volume, increase in volume is given by this. Okay, so next delta V is equals to, this is nothing but the coefficient of cubical expansion. Okay, now same thing will be applicable for that. That is nothing but the delta V is nothing but the final volume minus initial volume. Then again original length, it is V0, again multiplied to the delta T. Okay, so this equation we can also be written as delta V upon, okay, then the coefficient proportionality constant is given by V0 gamma delta T. Delta V is given by this equation. Then next, value of the gamma depends upon the material used and the temperature given to it. Okay, so gamma is equals to V minus V0 upon V0 delta T. Okay, you can also write it as a V2 minus V1 upon everything is same as it was in a surface area. Okay, so now here one small graph is there. that is variation of gamma with respect to the temperature. Okay, so what was here, what is the change here? There is no change between the superficial expansion and the cubical expansion. Everything is similar to that, but the volume is denoted by the alphabet V. Okay, actually the three dimension is there. And now we will see the variation of gamma with respect to the temperature. Okay, so here one graph is there that we are going to study. Okay, on the x-axis it is nothing but the temperature. Why we are writing the temperature? Because this is the temperature in Kelvin. Why we have chosen this on x-axis? Because temperature is only the cause for the change in the respective areas. Okay, and here on the y-axis, gamma is in 10 to the power minus 5 Kelvin inverse. Okay, here on y-axis, gamma is 10 to the power minus 5 Kelvin inverse. Okay, these 3 and 6 values are in that range. So from this graph, what we are going to study, or what we are going to understand from this? The first thing, that the variation of gamma with respect to the temperature. If the temperature changes for the typical materials or the solid which we are talking about, what is the variation of gamma that we are going to see over here? So what is here? So the gamma depends upon the temperature of the given substance, and it is different for different substance at the same temperature. Okay, here if temperature is same, okay, temperature will be same, but the value of gamma will be different for different substances. Different will be different for different substances. Okay, this is the basic change regarding the gamma which we are discussing about. So gamma becomes constant at a certain high temperature. So at a certain high temperature, gamma is going to become constant. Means what? I think after 500 Kelvin, it is going to become constant. And gamma are generally small. The value of gamma is small. Okay. Next is materials like Pyrex glass and inver. Okay, so these materials suffer much less thermal expansion than others. Okay, so these are the two materials which suffers less thermal expansion than others. Okay, so this thermal expansion can also cause some error there. Okay, as they are causing um, volume change, there will be one sort of error. For example of this, or in order to understand this, or in order to explain this concept that the thermal expansion also causes error in the practical or the experimental things, is that the simple pendulum. Okay, in the case of the simple pendulum, the same thing is happening there. Because of the temperature, there is the change in the length, and because of that, the experiment do not get the correct values there. Okay, okay, so in order to overcome that difficulty, we use the this gamma term there. Okay, so this was the concept, or these were the, and this thermal expansion, there is thermal stress also. Okay, so I think this is more than enough for you, and you can write it of your own also, that stress and strain you have already studied, and you can apply the concept of your own. So this was the one dimension, two dimension, three dimension thermal expansion respectively, and the four different scales with their divisions and everything we have completed. Okay, then we'll go for the next article which is there in your syllabus.